All right. So that's worth making as a remark. And that remark is that the local definition of basis functions leads to global basis functions okay. Global basis functions associated with each node, say XE, all right. So if we look at the global basis function associated with node E, that global basis function has compact support right in elements omega E minus 1 and omega E, sorry, not omega E plus 1, should be just omega E in this case. Okay. Now the fact that this is global basis function is associated with the elements adjoining a given node will be observed in higher dimensions as well. Okay. Of course, in higher dimensions, it won't be just to the right and left. It will be, they will be neighbors in other directions as well. Okay. All right. Fine. So this is another property of the types of basis functions we are defining. So now with all of this in place, we have a clean way to write out our trial solution as well as our weighting function. Okay, and it's useful now to go back and recall from the types of integrals that we need to evaluate in the Galerkin weak form, just what we need to do with these finite dimensional functions. Okay, so let's recall. So the kinds of integrals we need to assemble come from the fact that we have an integral, we have a sum over E of an integral over omega E of a function of this type, right? The gradient of our weighting function times sigma h a dx equals sum over E integral over omega E WH F. It's worthwhile remembering that X is a function of, F is a function of, is defined with respect to X, which in turn can be parameterized in terms of, parameterized by Xi, right, using our bi-unit domain. Okay, this times A dx plus WH at L T A, there's no dx there. Okay, so these are the integrals that we need to compute using these finite dimensional functions. Now, one more thing I need to state as we go on, okay, and that is the following. An important note to make is this. Okay. Consider element 1 in omega E for E equals 1. Okay. If we have that as our domain, and let's suppose that this is omega 1. Okay, the very first element. We know that this point here is x1, which in this case, because of the way we're setting up the problem, is the point 0, right? And this is global node number x2. Okay, Recall that here we have a Dirichlet boundary condition, right, at x equals 0. So out here we know that UH equals 0, right? It's equal to U naught, but then actually let's just leave it as U naught. I'm sorry, I'm getting ahead of myself by saying that's 0. That's U naught, okay? And yes, we know that if we're thinking of this bar, thinking of it as an elastic bar, and if it is fixed on the left, that U naught will indeed be 0. But for now, let's just leave it as U naught. Okay. So that part is straightforward. What about WH? There. What should happen with the weighting function at that point? Because it corresponds to the Dirichlet boundary condition. Right? There's something special that happens to it. Think about it. Yeah, WH goes to 0. Okay? Always. Now, it does not matter what the actual value of U naught is. I know I got ahead of myself a couple of minutes ago and said that U naught is equal to 0. It often is. Even if it were not equal to 0, the fact that you have a Dirichlet boundary condition there implies that WH has to be equal to 0. Okay, that's how we've constructed our weighting function space. What this tells us is that as far as the field WH is concerned within this element, we only truly need that basis function. Okay, because we are already going to make sure this, in fact, choosing just a single basis function allows us to ensure that WH does indeed vanish at x equals 0. Okay, and in particular we choose only n2 to be a basis function there. Okay, so what this says is that now if I just pull out that element, right, omega 1, because we know that at WH at 0, at x equals 0, has to be equal to 0. What it tells us is that the only basis function we need in that element is n2. Okay, n2 of x is only basis function fn, short for function, for representing the weighting function. Okay, it's not the case for the trial solution. Only for the weighting function, right, do we need a single basis function. So n2 of x is only basis function needed for WH of x for E equals 1. Okay, that's something to observe here. Right. However, for any other element, E equals 2 and so on, right up to number of elements in the problem, we have properly WH of x sub E equals sum A going from 1 to number of nodes in the element n A x d A E. Okay, for WH of x where E equals 1, we don't need a sum, right? We have a single basis function. We just have that. And I realized that I used D here. We are using C to write out the degrees of freedom corresponding to the weighting functions. Okay? So there is a difference in the way we choose to interpolate or to represent our weighting function depending upon the elements. Okay? As something to think about, what if we had another Dirichlet boundary condition in our problem? What if we had a Dirichlet boundary condition on the right end as well? Then for that element also we would do the same sort of thing, right? We would use only a single basis function for that one. Okay, so that's just something to keep in mind. I won't develop that idea right now. We'll come back to it when we need it. Okay, but that's just something to keep in mind. Okay, what I want to do as well is look at what we need for our finite dimensional functions, right? Let me just do this for you. Just go back to this the previous slide and recall that when we look at this finite dimensional weak form that's written just below the word recall, you observe that we have to compute a gradient of our shape function. Furthermore, you observe that sigma h is defined as E times UH comma x. Okay, so we see the need to compute gradients of our functions. Here, however, we do not need anything. We do not need to compute gradients, right? And there we just need to evaluate the function at L. Okay? At any rate, what this tells us is that we need to compute or calculate WH comma x for the weak form, and we also need to compute UH comma x, and in particular UH comma x is needed for computing the stress sigma h. Okay, so how do we go about doing this? Easy enough. Let's just recall that, again, taking advantage of the fact that we have a local representation, right? So we can look at our trial solution in element E, in a general element E, and so I will write it as, sorry, not a summation over E, but a summation over A. Summation over A, 1 to number of nodes in the element, N A, I will now write it as a function of C. Okay? We know that we originally defined it as a function of x, but then by going to our bi-unit domain, we observe that it's more convenient to write it as parameterized by C. Okay, we have this D A E, and we also have WH of E. Function of C is also equal to sum over A NAC C A E. Right? Well, we also need to compute those components, right? And the way we can do that is just by computing NA comma x in both those expressions, right? Because the DAEs and CAEs are just degrees of freedom, right? They do not have any dependence upon position, right? So we observe that in order to compute these gradients of the trial solution and of the weighting function, we just go to our representation for the corresponding functions. We essentially need to compute gradients of our basis functions. Okay, so how do we do that? Well, we just invoke the chain rule, right? So sum over A right. So now we write NA comma x as NA comma C comma x D A E. Okay, and this quantity is done in exactly the same way. Sum over A NA comma C, which is easy to compute because we are indeed actually defining the NAs as being parameterized by C. Okay, this times C comma X, C A E. Okay. Now this is useful, right? Because it tells us how we can compute our gradients of required fields, except for the fact that we may say, well, how do I actually go around computing that quantity? How do I write the derivative of my position in the bi-unit domain with respect to my physical coordinate x? Okay. Think about it. We'll come to it, but we will do it in the next segment.